Welcome to our quantum deep dive. Today, we're plunging into one of the universe's really big questions, drawing insights from a fascinating essay by Yorgos Nepat called Leptogenesis, Schlüssel zur matter-antimatter asymmetry. Have you ever just looked up at the sky and wonder, well, why is there anything here? Stars, galaxies, us. Because the universe we see, it's just overwhelmingly made of matter.
Right. It's not this 50-50 split of matter and antimatter you might initially expect.
And that imbalance, it's fundamental. It's what we're going to try and unpack today.
Yeah, and it's crucial because if you did have equal amounts back in the early universe, poof, they would just annihilated each other, leaving behind basically a universe filled with light, like photons and maybe some neutrinos.
So no stars, no planets.
No complexity at all, certainly no life. Our existence is basically thanks to this slight imperfection, this asymmetry.
So our mission today is to explore leptogenesis. It's the leading theory for how this whole thing got started. And we'll also touch on some surprising connections, not just to the Big Bang, but maybe even to future quantum technologies. Should be interesting.
Definitely. Lots to dig into.
Okay, let's start right there. If the universe started out, let's say, perfectly balanced, how did we end up with all this stuff? What exactly is leptogenesis? What's the name mean?
Sure. So leptogenesis, it combines lepton, like electrons and neutrinos, those fundamental particles.
Right.
And leptogenesis, meaning creation or origin.
Yeah.
So it's describing processes very, very early on, like fractions of a second after the Big Bang, processes that led to this slight imbalance, an asymmetry between leptons and their antimatter counterparts, the leptons. This whole idea really started gaining traction, I'd say, the 70s and 80s.
Oh, really? So it wasn't always obvious.
Well, people knew about matter, but really grappling with the imbalance and its implications, that took time. And by the 80s, theorists were proposing that, hang on, maybe you need this lepton asymmetry first, as a kind of necessary precursor to get the baryon asymmetry, the proton and neutron imbalance that we actually observe today.
Ah, okay. So one leads to the other. You need the lepton imbalance first.
Exactly. It sets the stage.
Okay, now here's where it gets really interesting for me. How did they think this imbalance could even happen? What conditions do you need?
Right. You can't just magic it up. You need specific conditions. Andrei Sakharov laid these out back in the 60s, actually. They're called the Sakharov conditions. Think of it like a recipe. First, you need to be able to violate baryon number or lepton number. Basically, the total count of matter particles isn't absolutely fixed. It can change.
Okay, that's already outside the basic standard model, isn't it?
It is, yeah. That's key. Second, you need violation of C and CP symmetry.
C and CP symmetry.
Right, it just means particles and their antiparticles don't behave as perfect mirror images, especially in how they decay. Imagine, like, one particle decays into matter slightly more often.
Then its antiparticle decays into antimatter.
Precisely. That tiny preference, that CP violation, is crucial. And third, all this needs to happen when the universe is out of thermal equilibrium.
Meaning?
Meaning it's changing rapidly, expanding, cooling down fast, not just sitting there in a stable state. And then scientists like Fukujita and Yanagita built on this. They developed models specifically involving very heavy neutrinos called Majorana neutrinos.
Majorana neutrino?
Yeah, and that was a huge step. It started to directly link the tiny neutrino masses we observe today with this whole leptogenesis idea. It provided the first sort of concrete theoretical framework.
Okay, you mentioned heavy Majorana neutrinos. Let's pause there. What are leptons generally, and why are neutrinos suddenly so important here?
Sure. So leptons are fundamental particles, part of the standard model. You've got electrons, muons, tempus, and then their neutrino partners.
The ghostly ones.
The ghostly ones, exactly. They don't feel the strong force that holds atomic nuclei together. And neutrinos are super important because we discovered something amazing. They have mass.
Which wasn't expected initially, right?
And not at all. It was assumed they were massless for a long time, but they have a tiny, tiny mass. It's incredibly small, but definitely not zero. And that changes everything.
How do we even know they have mass? They're so hard to catch.
Good question. The evidence is rock solid now. It comes from neutrino oscillations. As neutrinos fly through space, say from the sun, they actually morph between their different types or flavors, electron, muon, tau.
They change identity.
Kind of, yeah. This mixing is described by something called the PMNS matrix. But the crucial point is, this oscillation, this flavor changing, can only happen if they have mass. Massless particles couldn't do it.
Wow. Okay, so these tiny, tiny masses, how on earth do they connect to explaining why the whole universe is made of matter? That feels like a huge leap.
It does, but it's where the theoretical physics gets really elegant, I think. The most popular explanation for why neutrinos have such tiny masses is called the seesaw mechanism.
The seesaw mechanism, like a playground seesaw.
Exactly like that. Imagine the light neutrinos we see are on one end, pushed way up high because they're so light. For that to happen, the mechanism predicts there must be partner neutrinos on the other end of the seesaw that are incredibly heavy.
Balancing it out.
Balancing it out. And specifically, these are predicted to be right-handed Majorana neutrinos. These heavy guys are absolutely central to leptogenesis.
Okay, Majorana, what's special about a Majorana particle? That sounds important.
Oh, it's fundamental. A Majorana particle is its own antiparticle.
Wait, what? How does that work?
It's bizarre, right? Imagine a particle where its antiparticle is just another version of itself. This property is critical because it allows them to decay in ways that violate lepton number conservation.
The first Sakharov condition.
Precisely. You need that lepton number violation. These heavy Majorana neutrinos, maybe with masses like billions or trillions of times heavier than a proton, would have existed in the very hot early universe. And their decays are thought to be the main event that created that initial lepton surplus.
Okay, so these super heavy Majorana neutrinos are decaying, but why doesn't that just produce equal amounts of leptons and antileptons? How do you get the asymmetry?
Excellent question. That's where the other Sakharov conditions come back in. Two things must happen during these decays. First, as we said, lepton number violation. Their Majorana neutral allows this. Second, you absolutely need CP violation in those decays.
The particle-antiparticle difference again.
Exactly. The probability of a heavy neutrino decaying into, say, a lepton plus a Higgs boson has to be slightly different from its probability of decaying into an anti-lepton plus an anti-Higgs. It's a minuscule difference, maybe tiny, described by this parameter epsilon of Freckon Dammit. But you have gazillions of these decays happening in the early universe, and that tiny bias adds up, creating a net excess of leptons over antileptons.
And where does the Higgs field fit in? The famous mass-giving particle.
The Higgs is essential. It interacts with all fundamental particles that have mass through what's called the Yukawa coupling. That's how electrons get their mass. And through the seesaw mechanism, the Higgs interaction is also responsible for giving the light neutrinos their effective masses. There's a neat little formula. The light neutrino mass is roughly the square of the Yukawa coupling times the square of the Higgs field value, divided by the mass m of the heavy Majorana neutrino.
So wavy m.
Right, and it shows that seesaw effect beautifully. The bigger m the heavy neutrino mass is, the smaller the light neutrino mass becomes. The Higgs connects it all.
Okay, I think I'm following. We've got heavy Majorana neutrinos decaying, violating lepton number and CP symmetry thanks partly to the Higgs, creating a small surplus of leptons.
You got it. That's the core idea of leptogenesis.
But we live in a universe made of baryons, right? Protons and neutrons, atoms, stars, us. How does an excess of leptons turn into an excess of baryons?
Ah, yes. The grand finale, in a way. This involves another really cool kind of weird process called stellaron processes.
Stellarons, okay, what are they?
They are these non-perturbative quantum field theory transitions. Think of them as sort of energy pathways that were active only when the universe was incredibly hot and dense before the electroweak symmetry breaking. What's absolutely crucial about stellaron is that they can change both baryon number B and lepton number L.
They can create or destroy protons and leptons.
Effectively, yes. But, and this is the magic trick that can serve the difference, B minus L.
B minus L stays constant.
Exactly. BL is conserved by sphalerons. So if you start with a non-zero L, or a lepton asymmetry from leptogenesis, and 0B, the sphalerons will try to equilibrate things, converting some of that lepton asymmetry into a baryon asymmetry while keeping BL constant. They act like a cosmic converter.
Wow, so there's a direct conversion rate?
Yep. The math works out pretty cleanly. The final baryon asymmetry B is approximately related to the initial lepton asymmetry L by the formula B, L 2879.
L minus 20 over 79.
Right. The minus sign just indicates whether you get matter or antimatter depending on the sign of L. But the point is, you generate a baryon asymmetry automatically from the lepton one. That's how we get the matter surplus we see today.
That's really elegant. But it highlights something important. The standard model alone can't do this, can it?
Absolutely not. And that's one of the most compelling things about leptogenesis. The standard model doesn't have enough CP violation, and it conserves B and L perturbatively. Leptogenesis requires physics beyond the standard model. It needs those heavy Majorana neutrinos from the seesaw mechanism. It needs new sources of CP violation. It needs those non-equilibrium conditions.
So it points towards bigger theories.
Definitely. It fits naturally into frameworks like grand unified theories, GUTs, or theories involving supersymmetry, maybe even string theory. It suggests the standard model is just, one piece of a much larger puzzle.
Okay, now for the real curveball you mentioned earlier. The essay connects leptogenesis to quantum technology. How on earth does something from the Big Bang link to quantum computers?
It sounds wild, I know, but the connection is in the underlying physics concepts and mathematical structures. Things like CP violation, the role of topology in processes like Sphaler transitions, non-abelian gauge fields. These concepts aren't just cosmological, they have direct analogs in condensed matter physics, the study of materials. Think about exotic states of matter like topological insulators or Weil semimetals.
So the maths is similar, or the principles.
Both, in some ways. The fundamental ideas about symmetry breaking, about how certain states can be topologically protected, or how particle-antiparticle distinctions behave, these themes echo across fields.
So could studying leptogenesis actually inspire, new quantum devices?
That's the exciting prospect. Understanding how the universe created and preserved an asymmetry, or how sphalerons mediated topological transitions while conserving BL, that kind of thinking could potentially inspire, say, new error correction codes for quantum computers, maybe ones based on topological principles. Or think about Majorana fermions again. The heavy ones are key to leptogenesis. But physicists are also trying to create their analogs in superconductors.
Right, for topological quantum computing.
Exactly, because those Majorana states in materials are predicted to be inherently resistant to certain kinds of errors. So studying the cosmic version might give us insights for the lab bench version, and vice versa. It's about the fundamental principles crossing scales.
That's fascinating. But okay, let's be realistic. How do we actually prove leptogenesis happened? We can't exactly build a time machine.
That is the multi-billion-dollar question. It's incredibly challenging. Direct observation is pretty much impossible.
So we look for clues elsewhere.
Indirect evidence. Smoking guns. One major area is neutrino physics itself. Experiments like DUN and Hyper-Kamiokande are designed to precisely measure CP violation in the light neutrinos we see today. If they find CP violation there, it doesn't prove leptogenesis, but it shows that leptons do violate CP symmetry, which is a necessary ingredient.
Okay. Well,
We can search for signs of those heavy neutrinos, maybe not the super heavy ones, but potentially lighter versions, at particle accelerators like the LHC. And cosmology gives us clues too. Looking closely at the cosmic microwave background radiation might reveal subtle hints about the nature of the primordial asymmetry. Oh, and a huge one would be detecting something called neutrinoless double beta decay.
what's that?
It's a hypothetical type of radioactive decay that can only happen if neutrinos are their own antiparticles if they are Majorana particles. Finding that would be revolutionary. It would confirm the Majorana nature needed for leptogenesis.
So what's the outlook? Where does the research go next?
It's pushing forward on all these fronts. We need the next generation of bigger, more sensitive neutrino experiments. We need higher energy colliders, like the proposed Future Circular Collider, the FCC. We also need advances in theoretical modeling and maybe even quantum simulation to explore these scenarios. If we could directly detect one of those heavy right-handed Majorana neutrinos, or observe neutrinoless double beta decay, that would be absolutely groundbreaking evidence supporting the whole picture.
Wow. What an incredible deep dive. We've gone from why we exist at all, through the intricate physics of the early universe guided by Yorgo Schneppat's essay, right to the frontiers of particle physics and even potential links to future tech.
It really shows how interconnected physics is. This quest to understand the matter-antimatter asymmetry, it pushes our understanding of cosmology, particle physics, and it unexpectedly might even feed back into quantum technologies. It's a fundamental question with really far-reaching implications.
And just think for a moment. Imagine that perfectly balanced universe where matter and antimatter wiped each other out. Just radiation, no stars, no planets, no chemistry, no us sitting here wondering about it.
Our existence hinges on that tiny initial imbalance, amplified by these incredible processes like leptogenesis.
Makes you wonder, what other subtle imbalances or hidden symmetries might be shaping the universe in ways we haven't even conceived of yet?
Absolutely.
Yeah.
There are likely more surprises waiting.
Well, we hope this discussion has sparked your curiosity as much as it has ours. If you want to explore more about leptogenesis and the work of Yorgo Schneppet, you can find more at schneppat.de. Until next time, keep exploring.
And keep asking those big questions. Goodbye.